Okay, welcome to this additional set of slides for your course on advanced communication systems. So the topic that we are going to do today is on the pre-processing block of the OFDM, or the orthogonal frequency division multiplexing. So we'll be doing with two techniques, one which is known as the crest factor reduction, or commonly called as the PAPR reduction, and the second one which is called as the digital predistortion. So we'll start off with some basic block diagrams of OFDM and then explain about the methods that are going to be used for performing this crest factor reduction as well as the digital predistortion. So an OFDM stands for orthogonal frequency division multiplexing, and it is a multiplexing technique where we convert a time domain signal into its frequency domain so that it can tolerate the errors and the frequency changes that are produced due to the frequency selective nature of the multiple access channel or your multipath channel. So the block diagram of the OFDM transmitter is represented here on the slide. You can see that we feed the data bits first to a serial to parallel converter, where the bits in series are converted into parallel to take an endpoint constellation and to compute the endpoint IFFT. So what we consider is we are going to convert the time domain into the frequency domain, and at the receiver we convert the frequency domain again back to the time. So once it is fed into the IFFT block, the IFFT block computes the inverse Fourier transform, and later it is fed to a parallel to serial converter, where all the bits are now appearing as serial, and it appears through two of the channels which are represented by the in phase and the quadrature parts. The in phase and the quadrature parts and then mixed to the RF and then transmitted over the air for the other receivers to receive this. Now the OFDM signal is characterized by many frequencies, usually called as a multi-carrier technique. OFDM uses multiple carriers in order to modulate the data. The time domain signal is actually being represented in the frequency, thus the signal amplitudes becomes frequency components. Next we discuss about the PAPR, what is meant by the PAPR and what is its relationship with the crest factor. So the PAPR of a signal is representing the peak to the average power ratio, which means that it is a measure of actually how much power is going to overlap with the other frequencies after the power amplification stage of the OFDM. And the crest factor is nothing but the root of the PAPR, or we can write the crest factor to be in terms of the amplitude, which is the maximum over the RMS, and the PAPR is C squared. So the square of the amplitudes will give you the power, and that is why peak to average power ratio, or PAPR, is C squared. Now the table below actually shows the PAPR values of some common waveforms. So first you can see a DC. So for a DC signal, both its maximum as well as the RMS values or the amplitudes are the same, and hence the crest factor is 1. Or if I represent PAPR in decibel scales, note that there is a small correction here. dB, B should be capital. So for the DC, PAPR is 0 dB. When you take a sine wave, the maximum to the RMS value takes the value of root 2, because for the sine wave of amplitude 1, the RMS value is 1 over root 2, and hence the crest factor is root 2, and PAPR is approximately 3 dB. Now going to 64 QAM, or the quadrature amplitude modulation, we get a slightly greater PAPR of 3.7 when it reaches WCDMA, or the wideband CDMA, which is essentially what is used in our 3G systems. The PAPR rises to around 10.6 dB. And when it comes to the 4th generation OFDM, or the OFDMA, where it is commonly known as, the PAPR rises to about 12 dB. Now this PAPR increment with each technology is a serious issue for a designer, and hence every designer is looking to minimize the PAPR by doing some reduction techniques, which are commonly known as the crest factor reduction. Now we will see the reason for going for techniques that should reduce the PAPR, or what is the motivation for reducing the PAPR of a given waveform. So if you take a linear system and feed a frequency of f0 through this linear system, at the output of the system we are going to get the same frequency f0, because the linear system has got the property that the eigen function corresponding to the system is the complex exponential, or it does not alter any frequencies. Now when we feed the same f0 into a nonlinear system which obeys the square law, so square law essentially means that the frequency or the frequency components appears as that in a square wave, or what it means is that every odd harmonic of f0 appears at the output. So in addition to the f0 frequency, you are going to get the corresponding odd harmonics of f0, which are 3f0, 5f0, and so on. Now here is a graph which is showing you the gain characteristic of a power amplifier. So the gain characteristic essentially means that it plots the input amplitude range versus the gain in decibels. So what it says is that this gain characteristic should be ideally a straight line, which is 45 degrees probably, and or 45 degrees or according to the gain that it should give you. Or if I plot this in dB, I should get a smooth constant line, so that means the gain should be a constant one in the ideal case. But what happens to practical power amplifiers is that after a particular dynamic range or after a particular range, input range amplitude, there is a small change in the gain, and essentially it is a spillover of the amplitude into the other sidebands in the OFDM system. Okay, so here is what we just explained in the previous slide. So essentially the dynamic range is the range of values of the signal that appears at the input stage of the amplifier, or what is the range of amplitude, maybe in volts, that is happening in the input of the amplifier. So if there is a V min which represents the minimum voltage at the input, and V max which is the maximum voltage at the input, then 20 log of V max by V in is known as the dynamic range. And as the dynamic range increases, what happens is that the linear nature of our amplifier is going to be modified into a non-linear one, and hence more frequency components are going to be generated due to this non-linearity. Now for a typical WCDMA system or a 3G system, the bandwidth of the system is 3.84 megahertz and the carrier spacing is 5 megahertz. So 3.84 megahertz is the bandwidth of a single carrier, and you will have multiple carriers around this. So if you are using ideal filter with 4 carriers, 4 multi carriers, for the linear case your total bandwidth is coming up to around 19 megahertz. But suppose there is a single intermodulation or the non-linearity of first order. If it happens, you will have the third harmonic also being coming at the output, and hence there is a total bandwidth of around 28 megahertz, which is around plus 10 addition in the bandwidth with a single order modulation increase. So which means that you can consider with each added block the total bandwidth is actually doubled. Now we are going to see how we are going to limit this overlap of amplitudes into the other frequency band when you're performing OFDM. So the simplest thing that you can do is reduce the dynamic range, and by reducing the dynamic range, what we mean is that whatever amplitudes are going to overshoot the required range, the required linear range, are going to be clipped. So we are going to learn about 2 crest factor reduction techniques which are actually based on clipping of the waveforms. So whatever amplitude that happens, above a particular amplitude which denotes the linear range is going to be threshold into a constant. So the first technique is called as the magnitude or the vector clipping, where the maximum amplitude that is allowed out of the system is some quantity A, and A is nothing but it is the square root of the I and the Q components, square of the I and Q components. So whenever the value of this x bar, which represents the magnitude of x, so please read this as x bar, it's not A. So whenever x bar rises over A, which is a maximum amplitude, you limit that to A, and whenever it is less than A, you take the same amplitude. So essentially that is a clipping. Now there is a second type of clipping which you can do, which is separately clipping out the I and the Q components. So the I component you separately clip it down to an amplitude range of A, and Q component also separately to an amplitude range of A, or absolute of I and Q separately needs to satisfy the condition that it should be clipped to a maximum value of A. Now another classification that we can do on the clipping technique is hard clipping as well as a soft clipping. So hard clipping is the typical clipping that we perform in any electronics lab, your clipping circuits. So there is a hard cutoff to the input voltage, and after this cutoff voltage, all your other voltages are clipped to that level. There is no more voltage that appears above the threshold voltage, and for this the leakage of the signal power beyond the desired bandwidth happens. So leakage is more for the hard clipping case. So leakages of the signal power. Now when we do a non-linear sort of clipping, which is also known as the soft clipping, so here we are going to do a non-linear clipping where there is no sudden threshold being applied, but we try to modify the gain of the signal in the other range also. So by introducing this soft clipping, we are going to adjust the gain of the system such that the output of the amplifier appears to have a constant gain. So currently this figure shows only two such gains, but there can be many thresholds that can be applied for soft clipping also. So high amplitude has got a reduced gain, because at high amplitudes you know that the power amplifier gain is going to reduce. Now next we are going to see about what is a predistortion block or predistortion techniques. So the digital predistortion basically implies that we are going to predistort the signal so that when it actually goes through the OFDM block, the distortion is minimized. Now what kind of distortions are going to appear in a system? So it can be either an amplitude to amplitude distortion or an amplitude to phase distortion. So basically there can be amplitude distortion as well as the phase distortion. So one way to test whether a particular circuit or a transmitter has a phase or a magnitude distortion is by actually passing some tone, some predetermined tone of frequency, say f. When you pass it over the system at the output, if this tone experiences an amplitude shift as well as the phase shift, we are going to apply this particular inverse of the amplitude and the phase shift such that the distortion of both amplitude and phase gets nullified when it comes out of the system. So a very good technique by which you can determine this is by giving some reference signals and identifying what are the corresponding amplitude as well as the phase distortions happening for each and every individual frequencies, and then applying an equalizer sort of mechanism where these are taken care of, and hence the overall system is free from all sorts of distortions or phase shifts and amplitude shifts. So the digital pre-distortion blocks can basically be applied at any of the stages, which can be at the RF or the IF or even the baseband. So the baseband pre-distortion is usually implemented in a DSP, and I and Q components are dealt separately in these pre-distortion blocks. So while doing this pre-distortion, the dynamic range is increased in the process. So always we would like to have the crest factor reduction to follow the pre-distortion block, because we know that as the dynamic range increases, the PAPR is going to come into effect, and hence over-modulation or higher order intermodulations are going to play a role. So usually the pre-distortion blocks comes first and then followed by crest factor reduction blocks. Now the pre-distortion is a sort of inverse estimation where you actually estimate for each frequency what is going to be the amplitude and the phase change, and you are going to apply an inverse filter to rectify these errors that are forthcoming. Now here is a typical block diagram showing you the digital pre-distortion block along with the power amplifier. So you can imagine that the crest factor has not been incorporated into this diagram. So the first case actually represents the baseband case where our signal, the input signal or the input power, is amplified by G. So if you write the power in dB, the output power is Pin plus G. Now when you introduce the pre-distortion block also, there should not be any change in the gain of the system. So the gain of the system should not be altered by the digital pre-distortion block. Or if you are going to consider this as a filter, the digital pre-distortion network or the filter is going to be an all-pass filter of unit gain. It's a filter that passes every frequency through it with a unit gain. So only alteration it is supposed to do is on the case of phases. And here is how we are going to do this operation. So basically the pre-distortion in the digital domain is implemented using a lookup table. So this lookup table stores the value of the I and the Q distortion separately, where I represents the I channel and this is the pre-distortion network. The ith symbol that is going to pass through this is going to be given this factor, which is 10 raised to gain in dB by 20. So that is to reduce it to the gain in voltage out by voltage in into cos of negative inverse phase modulation of the ith component again by 180 into pi. So it is a degree to radian conversion. So inverse phase modulation is actually in degrees. Similarly for Q, here you should multiply by the sine of the component. So the inverse estimates that are actually being computed is the inverse phase modulation as well as the gain of the predistortion network. Now finally you can see that the frequency response after and before the predistortion are completely different. You can see the change. So the blue curve over here represents the power amplifier output alone without keeping any predistortion block. So you can see that block diagram that I have shown 2 slides before, where there is no predistortion network. So you can see the blue curve over here